These are what we want to predict using our stacking regressor model. Think of them as the answers we're trying to get our model to learn. I'm training the model to accurately predict house prices, you see. It's like a fun house price guessing game. After I train my stacking regressor model, these are the house prices the model predicts. These are the model's guesses, based on what it's learned from the training data. I'll compare these predictions to the actual house prices to see how well the model performs. The closer the predictions are to the actual prices, the better the model is doing. This is the dataset I use to teach my stacking regressor model. It includes information about houses, size, location, features, etc., along with their actual prices, the answers. I use this data to train each base estimator and then the meta-learner, final estimator. It's like showing the model lots of example houses and their prices to help it learn how to guess the prices of new houses. This is a repetition of the previous row, which shows that the stacking regressor model gets its training data again. I use this data to teach my stacking regressor model, including the base estimators that make it up. This is where the model learns to make its predictions. I'm using 3 different models to predict house prices: linear regression, random forest regression, and support vector regression. These are my base models, each trying to solve the problem on its own. Each base estimator makes a prediction for each house's price. I'll then use these predictions as input for my final model. This is my final model, the star of the show. It takes the predictions from my 3 base estimators and learns how to combine them to make the best prediction. This is one of my base estimators. It tries to find the best fitting line through the house price data. Another base estimator. It works by finding the optimal hyperplane to separate the data. Yet another base estimator. It uses lots of decision trees to create a more robust prediction. The ultimate goal: to accurately predict the price of a house using the power of ensemble learning. This is the gradient boosting regressor model that combines the predictions of the base estimators to make a final, hopefully more accurate, prediction of house prices. It's the key to stacking. Think of it like a team. My base estimators are like individual players, each making their own prediction. The final estimator is the coach who sees all those predictions and makes the final decision. I'll use this data to train all my models, both the base and final models. I see predictions as the outputs from each of the base estimators: linear regression, random forest, and support vector regressor. These predictions are crucial because they become the input data for the final estimator, the gradient boosting regressor. Think of it like this: each base estimator gives its best guess at the house price. The final estimator then uses these guesses to make its own, even better, prediction. This is one of the base estimators. I use it to fit a straight line to the relationship between features and house prices. It's a simple, yet often effective model. This is another base estimator, and it's more complex than linear regression. It works by building multiple decision trees and combining their predictions to improve accuracy. I find it helpful to think of it as a wisdom of the crowds approach. This is the third base estimator. I use support vector machines to find the best hyperplane that fits the data and predicts the house price. This is an algorithm that is very effective when your dataset has many features. It's a powerful tool in my arsenal. This is the meta-learner, also known as the final estimator. It uses the predictions from the base estimators as input. I find this step very important, because it combines their strengths and hopefully produces an even more accurate prediction. These are the individual machine learning models: linear regression, random forest regressor, and support vector regressor, that I use to predict house prices independently. Their predictions are then combined by the final estimator. This approach leverages the strengths of various models. This is the dataset I'll use to train each of my models. I'll use the same data for each base estimator. This ensures that all predictions are made based on the same data. I use a stacking regressor to combine the predictions of multiple machine learning models. It's like creating a team of experts and having a final decision maker that weighs their opinions. This is the ultimate goal: to accurately predict house prices using my stacking regressor. I aim for the best prediction possible by combining the predictions of several different models. I see 3 base estimators here: linear regression, random forest regressor, and support vector regressor. These are individual machine learning models that will independently learn to predict house prices from your training data. Think of them as individual experts, each offering their own price prediction. This is the dataset you use to train all the models. It contains information about houses, like size, location, features, and their corresponding sale prices. Each of the 3 base estimators will use this same dataset to learn and make predictions. This is the gradient boosting regressor, which acts like a superlearner. It doesn't learn directly from the house data itself. Instead, it gets the predictions made by those 3 base models, the individual experts, and then learns how to combine those predictions for a better, more accurate overall house price prediction. This is a specific type of machine learning model that is used as the final estimator in this stacking regressor. It's known for its ability to combine predictions from multiple models effectively. After each of the 3 base estimators has been trained on the original house price data, they will each make their own predictions for the house prices in the training data. The gradient boosting regressor will then use these predictions as its input data to learn how to optimally combine them. The output of the entire stacking regressor is a single prediction of the house price. This is a combined or stacked prediction, resulting from the final model's learning on the predictions of all the base estimators. It's like a team effort, with the final model integrating insights from each of the individual experts. The ultimate goal: to accurately predict the price of a house. We use stacking regression to get the most reliable price prediction. I'm confident we'll get great results. This refers to the overall structure of using multiple base estimators whose predictions are then combined by a final estimator. It is a specific form of ensemble learning. It's a powerful technique to improve prediction accuracy. These are the outputs that each of the 3 base estimators, linear regression, random forest regressor, and support vector regressor, generate after being trained on the house price data. Think of them as individual guesses from each model about what a house's price should be. They become the input for the final estimator. Each base model provides a vote, and the final model weighs these votes to make a final decision. This is the gradient boosting regressor. It doesn't look at the original house data. Instead, it trains on the predictions we got from the 3 base estimators. It learns patterns from the votes of the base models and uses this knowledge to make a more refined prediction. It's like a superpowered judge weighing the opinions of the other models to reach the most accurate house price estimate. I'm using 3 different models to make initial predictions: linear regression, a random forest, and a support vector machine. These are my base estimators, like they are the foundation upon which I build my final model. Each one provides a unique perspective on house prices. This is all the information I use to train my 3 base estimators. Features like square footage, number of bedrooms, and location, paired with the corresponding house prices. I train each base estimator separately using this full dataset. After training my base estimators, I use them to predict house prices for each house in the training data. Each base estimator gives me a different prediction, which is kind of like getting 3 different opinions on a house's value. This is my final model, the star of the show. It takes the predictions from my 3 base estimators as input and learns to combine them into an even better prediction. Think of it as a super estimator that learns from the experts, the base estimators. It uses gradient boosting, a clever way to sequentially improve the predictions. This is a simple, yet effective, model that tries to find a linear relationship between the features and the house prices. This model uses multiple decision trees to make predictions, averaging their results to get a more robust and less prone to overfitting prediction. This is a powerful model that uses support vectors to define a hyperplane that best fits the training data to make predictions. This is the ultimate goal: accurately predicting the price of a house based on its characteristics. My stacking regressor combines the strengths of the 3 base estimators to hopefully create a superior prediction. I see these are the outputs from our 3 base models: linear regression, random forest regressor, and support vector regressor. Each model makes its own prediction for each house. We'll use these predictions as input for our final model. It's like getting expert opinions, and then having a super expert, our final estimator, weigh them to make the best decision. This is one of our simple, but effective, base models. It tries to find the best fitting line through our data points to make predictions. This is another base model that builds multiple decision trees and averages their predictions for a more robust result. Think of it like consulting many experts instead of just one. Here's our third base model, which uses support vectors to map the data into higher dimensions to find the best fit. This is good for complex relationships between the features and house prices. This is our final estimator. It's a powerful model that takes the predictions from the other three models, the base estimators, as input and learns to combine them to make an even better prediction. It's like having a top-level manager who takes all the expert opinions, analyzes them, and makes the final call. Pretty clever, huh? These are the three individual models that we train independently. Their predictions are the things we feed to our final estimator. This is the overall structure. We have the base estimators, like linear regression, random forest, and support vector, each making their own prediction. Then, the final estimator, gradient boosting in our case, learns from those predictions. Think of this as a team of experts working together. This is our ultimate goal. By carefully selecting our models and combining their power, we can create a high-performing stacking regressor to get the best house price predictions. This is our data set of house features and their corresponding prices. We use it to train the base estimators independently first. I see that you're looking at predictions. In this stacking model, the base estimators, linear regression, random forest, and support vector regression, each make their own predictions for the house prices. These are extremely important because the meta-learner, the gradient boosting regressor, uses these predictions as its input to learn. It's not training on the original house data, but rather, on what the other models have already predicted. It's like learning from experts. Pretty cool, huh? This is one of your base estimators. It's a simple, yet powerful model that fits a line, or a hyperplane in multiple dimensions, to your data. I expect you are familiar with this algorithm. Another base estimator, a random forest, combines many decision trees. Each tree makes its own prediction, and the forest averages those predictions for a more robust and less likely to overfit result. Random forests are known for their accuracy and ability to handle many features. This is also a base estimator. Support vector regression uses support vectors to find the best fit line for your data. It's particularly effective in high-dimensional spaces. This is your final estimator, also known as the meta-learner. It's trained on the predictions of the base estimators, linear regression, random forest, and support vector regression. It combines their strengths, hopefully improving overall accuracy. Think of it as a student learning from multiple teachers. These are the initial prediction models, linear regression, random forest regressor, and support vector regressor. They're all trained separately on the full dataset first. Then their predictions become the input for the meta-learner. This is the ultimate goal. You're trying to build a model capable of accurately predicting house prices. The stacking regressor is a tool to improve prediction accuracy compared to any single model. The initial data, which includes all the features relevant to the house prices. Your base estimators are initially trained using this data. This is the gradient boosting regressor in this case. It sits on top of the base estimators, learning from their predictions rather than the raw data. Think of it as an expert reviewing the work of junior experts and building a superior solution based on their combined work. This refers to the overall structure of your stacking model. It involves training several base estimators independently and then combining their predictions using a final estimator, the meta-learner. It is a powerful ensemble method used to improve model performance.